Well, I know.
Okay, we are now recording, I believe. All right.
Sweet.
What's up, Tyler?
That's sweet. I'll need it for
All
later.
right. So, for anyone who is deciding to watch this at a later time, this is either going to be posted directly to the group me, or I'm going to post this on YouTube and copy a link into the group me.
I have a question. When you record it, can they see the chat?
I don't know, but I'm going to be reading off the questions anyway, so they'll be able to hear it.
Do you think I'll get in trouble for this?
No,
Okay, cool.
I'm not giving it to Miss Robin if that's what you're asking.
I mean, if you're sticking on freaking YouTube.
It doesn't matter. Don't worry about it.
All right, we'll cut this beginning part in. Start now. And we are starting now.
All right. So this is also going to be this is for MSE-280 engineering materials review before the second try of the exam one, and also going over some topics for the first exam of CH 117 chemistry 2. All right. So we have some questions from the exam, which were acquired. Not going to say how, and I'm going to be going over those first. So, first question is, what happens to the strength of a thermoplastic polymer rope when it is pulled so that it gets longer and is plastically deformed in this way, but does not break? Does the strength increase, decrease, or stay about the same? In this context, it is strengthened. It is plastically deformed. This is strain hardening, basically. Same thing that happens to metals when you stretch out a thermoplastic polymer and you pull it out so that it stretches. What you're doing is, in a thermoplastic, it is primary bonds with secondary bonds holding them together. That's why it's able to bend in such a way. When you're pulling it and you're applying a force that causes it to plastically deform, you're actually stretching those atoms into more straight lines, aligning the primary bonds and making it stronger but less ductile at the same time. It's like Miss Robbins said, if you have a wire hanger, metal wire hanger, and you bend it a bunch of times, it's going to get harder and harder to bend each time. But this is, I'm trying to think of something else I could talk about here in the same context, something to relate in the last thermoplastic to. I guess imagine like you ever just had like one of those thick pieces of rubber and you pull it and you pull it and eventually it snaps, but the more you pull it, the harder it is to pull. I guess that's not a good analogy, but just know strength increases due to primary bonds becoming more aligned.
Becoming more what?
Aligned.
Gotcha.
So in a thermoplastic, it is primary bonds in kind of lines supported by secondary bonds. When you plastically deform it, you're pulling those covalent bonds, those primary bonds, into straighter lines. And when you do that, it allows them to get more aligned and become stronger in that way.
Okay, understood.
Select all the following that are usually multicrystalline. Going off of the study guide, multicrystalline are usually metals, ceramics, what else? Thermoplastics and elastomers can be partially crystalline. Usually it's thermosets, and thermosets are partially crystalline. Ceramics or well, what's the question again? What's it say? It keeps
That
going
are
down.
usually.
Are usually multicrystalline, so not singular crystalline. So yeah, that's right. It's going to be the multicrystalline ones are going to be ceramics, metals, and sometimes thermoplastic and elastomers are partially crystalline.
So, but like, those are partially, but would it fall under the usually? I don't know. Like,
If it has it listed, I don't know. I don't remember if it had it listed in the question, but if it did have those as one of the answer options, I'd select it because they can be
So-
partially crystalline.
so basically, the one you would select, if those were the choices, you would select metal, thermoset, and ceramic, just not glass and elastomer.
No, thermosets and semiconductors are crystalline, but usually semiconductors are usually singular crystalline. They're not multicrystalline.
Oh, okay.
Thermosets are usually amorphous, not crystalline.
Okay.
Also, amorphous ceramics are actually called glasses. They're like a subset. So that's why you say ceramics in their entirety when you say multicrystalline, because amorphous ceramics are called glasses. So a glass is actually a subset of ceramics that is amorphous and not multicrystalline.
Gotcha. So basically, I would just choose metal and ceramic. Got it.
Yes, because thermosets, plastic, and elastomers are typically amorphous, but they can be multicrystalline.
But we're just not going to worry about the can be.
Yes, but they're typically amorphous, and it's asking what's usually multicrystalline.
Gotcha.
A metal can be produced with a smaller grain size by solidifying it faster. Would you expect a metal that is solidified in a metal mold made of metal with a higher melting point than a metal being solidified, or in a ceramic mold to be stronger? Assume the two molds are the same size and thickness. Now, I actually thought about this, and I almost tricked myself on it. I initially selected ceramic mold because ceramics are typically used in metalworking. But if you think about what she said in regards to a thermos or a coffee cup, ceramics are good insulators. They help hold in heat and electricity. They don't conduct heat or electricity very well. Metals, on the other hand, conduct heat and electricity well. So the one that would cool off faster would actually be the one in the metal mold, because the metal would conduct the heat and allow it to cool off quicker, while the ceramic would help insulate it and keep it hotter longer.
Okay.
Okay, moving on. Select the metal crystal structure with the highest ductility. The metal crystal structure with the highest ductility is FCC, or I believe that's face-centered cubic. Yes, FCC is face-centered cubic, and that's the one with the highest ductility. The other two options are body-centered cubic and the one with the HCP. That one's going to be the lowest.
Sure.
And because it has the lowest ductility, it has the highest strength. Remember, ductility and strength are inverses of each other. If something gets more ductile, it becomes less strong. If something gets stronger, it becomes less ductile. All right. Any questions on that one?
Mm-mm.
Okay. What is the polymer type with primary bonds along the chains and secondary bonds between the chains? That's going to be a thermoplastic. Like I said earlier, when you stretch out thermoplastic, you align those primary bonds even more, and that strengthens it. And the secondary bonds within the primary bonds in a thermoplastic allow it to have some ductility. A kinky chain polymer is an elastomer. That's what allows it to be able to be stretched out so much and then still retain its original shape. It's all kinked up, and when you pull it, they unkink. And then when you release it, it rekinks. Like a rubber band is an elastomer. And a thermoset is going to be primarily primary bonds, primarily covalent bonds. And in terms of ductility, which is what this question is asking, it's asking what the polymer is with the lowest ductility. It's going to be a thermoset, because since it's mostly covalent bonds, it doesn't really have any wiggle room to move around like anything with secondary bonds or a kinked up polymer chain is going to be able to do. In terms of ductility, an elastomer is going to be highest, thermoplastic secondary, and then thermoset's going to be the lowest in terms of ductility. The addition of solute atoms to a metal alloy that increases the strength of a metal, I believe this is solid solution substitution. Hold up, yeah, I think it's solid solution. It may not be called substitution, but it's in line with solid solution, where you add stuff to a solid solution, such as impurity atoms, to strengthen the metal. This actually falls into two different categories. You have substitutional solid solution and interstitial solid solution. In a substitutional solid solution, solute atoms will replace the solvent in lattice positions. While in an interstitial solid solution, solute atoms will fit inside the lattice itself and not replace anything.
Okay.
All right. Plastic deformation in thermoplastic polymers is the result of blank. Like I said earlier, this falls in line with the first question and the ductility question. Plastic deformation in the thermoplastic polymers is where you're stretching it and you cause those covalent bonds to align themselves better. And once you do that, since covalent bonds are much stronger than the secondary bonds, and the secondary bonds are what allows it some ductility to kind of reform back into its shape. After you set those covalent bonds into stronger positions, they're not going to want to leave it. So for plastic deformation and thermoplastic, I'd say it's because the covalent chains are getting better aligned, in a sense. All right, moving on. Can ceramic or metals withstand higher temps? Ceramics, all the way. They can withstand much higher temperatures than metals and are usually used in metalworking. The type of bonding that best conducts heat is metallic. The reason being with metallic is that when a current, thermal or electrical, needs to flow through something, it flows through something using electrons. In an ionic bond, electrons are transferred between an anion and a cation. There is no electron for any current to travel through. The only time that there is a time for it to travel through with ionic bonds is when it's molten or in an aqueous solution. Those are the only times that an ionic bond can conduct. Covalent bonds also do not conduct heat or electricity because the electrons are shared. They're not moving around at all. It doesn't really have anything to flow through the current. Secondary bonds are secondary bonds. If you try and put a current through those, they're just going to break. The best choice for conducting heat and electricity is metallic bonds. What happens with a metallic bond is it's a bunch of cations surrounded by a sea of electrons, a bunch of loose electrons moving around, and that allows currents to flow through it readily. Any questions on that one? Once again, select the metal crystal structure with the highest ductility. I just answered that one. It is FCC, face-centered cubic, has the highest ductility, and HCP has the lowest. Materials of the exact same composition that are processed differently will have the same properties. That is incorrect. If they have the same composition, they may be composed of the same elements, but depending on how they're processed will change how the atoms are actually aligned in the material and can produce vastly different properties. And then there's select the metal crystal structure with the highest ductility. You just answered it, not going to answer it again. All right, so like I said earlier, metallic bonding does conduct heat and electricity the best because it has electrons for the current to flow through. I don't know how to answer 14. Ceramics have the more arrangements of atoms, right?
There's like a question. It was like select the following with the more ordered arrangements of atoms.
That's
I
going to
don't.
fall under anything that isn't amorphous, anything that's crystalline. Crystalline is having an ordered structure of atoms. Amorphous is stuff is kind of all over the place. That's why typically your plastics are amorphous. Ceramics are crystalline. If you're talking about an amorphous ceramic, it's called a glass.
So if I had like option choices, it would like glass would be one of the ones with the more arrangement of atoms, correct?
No, because
Oh.
glass is amorphous.
Okay,
Glass
so
is
we're going with the
amorphous.
amorphous ones.
Yes, it's if you're going for more arrangement, it's going to be whatever's crystalline, so metals and ceramics typically.
Okay, thank you.
What is fully amorphous? A thermoset or a glass is fully amorphous. And that's just it has no real structure and everything's just kind of jumbled together. Diamond and graphite are both composed of carbon but have drastically different mechanical properties. Select the following that are true. And diamond has a mix of ionic and secondary bonding. Diamond has a hexagonal structure. Diamond has covalent bonding. I can go ahead and tell you that diamond does not have ionic and secondary bonding. It is a carbon-based material, so it's going to have primarily covalent bonding. So that one's incorrect. I'd have to look up and see if it has a hexagonal structure. I'm not certain on that one either. The only one that I see is true is that diamond has covalent bonding. That is absolutely true.
I remember there's more like question. Obviously, there's more answer choices, and you were trying to find like what things were true. But can we go over some of like the facts about graphite and some of the things about diamonds, like their properties?
Okay, so graphite's the same stuff you have in your pencil lead.
Correct.
And its structure is what allows you to write on paper. It's layered in sheets held together by secondary bonding. When you rub your pencil against the paper, you're shredding off those sheets that will lay on top of the paper by breaking the secondary bonds. The sheets actually remain in their places on the paper. You cannot do that with a diamond, however. A diamond is one of the hardest materials. That doesn't mean that it's the strongest. You can break a diamond with a hammer, but it's the hardest, and that's due to diamond being primarily covalently bonded. It's hard. It won't bend at all. It'll shatter instead. But graphite has secondary bonds, so I'd say that's the main difference between the structure. Besides going into like the actual structures of them, is diamond is most definitely stronger than graphite due to it having covalent bonding, and graphite is weaker due to its structure and it having secondary bonds. For the next question, what type of bonding withstands heat? It's going to be both covalent and ionic bonds are excellent at withstanding heat. If you're going with overall all the time, it's going to be covalent bonds. An ionic bond will conduct heat if it's in aqueous or molten solution. However, a covalent will not. All right, any other questions?
There was a picture. I don't remember what the picture was of. I think it was a structure. Tyler, do you remember? Do you know what I'm talking about? Do you?
I do not remember.
Are you
Ethan,
alive,
did
bud?
you not get a picture or a structure or something?
I probably did, but I've definitely forgotten.
Oh my
Me too.
goodness. I don't remember.
All right,
I don't remember what
Tyler.
it was of. I just remember there's a picture and it was I don't remember now, honestly. It was asking if it was like face centered, body centered. Ring a bell, anyone? No?
Okay. So yes, that does ring a bell. So I'm guessing it had something like this right here. It had like, okay, you got a little box here, And you got your nice little boxes going over here. Boxy boy. Line across.
And
Had
then
something
had
like this, and then it had
yeah.
ball, 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 and then it had something like one here, and then like one over here, something like that.
I don't remember.
Well, this is an example of body-centered cubic. You have one. Wait a fucking minute. Brain working. I'm trying to remember if this is body or face. Let's look it up.
I think body centered is like the one where it's like perfect on every side and then just one in the center. I could be wrong though.
All right, yeah, there we go. Where is my drawing thingy? All right, so yeah, body centered is one in the center with all these kind of being drawn to it like that. This isn't a good sketch, I'm sorry, but basically that's in the center. Face centered cubic is where it is face-centered cubic is where it, like I drew it a second ago. So this is body-centered, and this one right here is face-centered.
Gotcha.
It's also going to have one over here and one over there, but you can't really see that because of the way I drew it. And this is face-centered cubic. And if you can't recognize hexagonal, I'm sorry, there's nothing I can do for you. Oh, look, more questions.
That was just the last one. That was like what you just explained.
What is the Bravas lattice for the structure? Yeah, you can tell from looking at the picture and looking back at the notes. This is still open notes now. This is just kind of supplementary stuff I'm doing right now.
Yeah.
But you can tell that it's going to be a cubic due to A equaling B and equaling C, and for alpha, beta, gamma all equaling 90. That's how you can tell it's going to be a cubic. All right. Any other questions regarding the engineering materials?
I think that's about it.
All right, then. Okay.